Okay, hello everyone. Welcome to day 2 of MBA 501. Can y'all hear me? Okay, I see 3 people smiling, so I assume that means everyone can hear me. So that's a good sign. Okay, I see some thumbs up. There we go. Are y'all excited for the day? Are y'all ready to go? Good, good. Okay, one sec. We have 4 people. Yes, very nice. Lots of people saying yes. Good to see that. Okay. So how this is going to work is I'm going to just lecture like normal. Keep your mic on mute. If you want to say something, feel free to unmute. You just jump in there. I taught a class online all summer, and that seemed to work out pretty well. So if you want to say something, if you want to interrupt, just feel free to interrupt. I will have the chat window open, so if there's anything you say in chat, I should be able to see it. But yeah, so that should be how this works. So thank you all for logging in to day 2. This is recording, so if you want to watch this later, that should be available. Keeping my fingers crossed. Okay, so what are we doing today? So today we are going to cover chapters 2 and 3. I know we're going to cover all of chapter 2. I'm hoping we'll cover all of chapter 3. We'll see what happens. If not, not a big deal, but that's going to be the goal for today. But first, some class things I want to note. So I created and uploaded all 5 homework assignments to Canvas. Yesterday, I worked all throughout the day to make your homework assignments available, and they are available to you now. So if you want to go ahead and do all 5 homework assignments, you could do that if you wish. The homework assignments should have the correct deadlines, so you should be able to log on and just see, when are they due. It's already listed on the syllabus, so there's no hurry to do them. There's no rush, but they are available if you want to do them early. And also you now have access to your group paper assignment. I did revise, or I don't think I revised it. I think I just changed the title of it. But the group paper assignment is available on Canvas, which, by the way, as a side note, sometimes I might accidentally say Sakai. Whenever I say Sakai, that just means Canvas. Sakai is what we used the past 4 years I was here. We're just now switching to Canvas. So if I ever say Sakai, don't think, oh God, what is that? Just know your professor has problems learning new things. Let's put it that way. Okay, so all your homework is available. Your group paper assignment is available. There is a small schedule update. So on the syllabus, I re-uploaded the syllabus. The syllabus is now correct on Canvas, but we are switching September 7th and 9th. One of the students in the class notified me that I scheduled the midterm on Labor Day. Obviously, I can't have a midterm on Labor Day. So now we are having no class on September 7th, and instead the midterm is on September 9th. So you have an extra 2 days to study for your midterm exam. I think that's the only thing to note about that schedule update. I think that's the only thing to note about the homework assignments. I will say with the homework assignments, it is a lot less work than prior years. Before, the homework assignments would be to do the analyses and then also write up a full report about them. I cannot grade a full report. So instead, the homework assignments are just do the analyses, type them into Canvas. So it is less work. I'm curious to see what the grades are going to be like, because before, some people that were weaker with stats could make up for it on the writing portion. Now, since I can only grade the stats part, We'll see what the grades are like. Of course, I do not want to guarantee this, but if the class average for this course at the end of the semester is a 20 or something like that, of course I'm going to curve. I'm not that cruel of a person. So we'll see what happens with that. Okay. Also, class format moving forward. I gave you all that survey to take about what your preference is for how many in-person classes. And it was almost equally split between none, 50-50, and all in person. I thought it was going to be more one way or the other, but I was astounded to see it's almost equally split. As you can see, 14 students said 0 to 3 in person, 13 said 4 to 8, and 16 said 9 to 12. If you run a chi-square test on that, the chi-square test is not significant, meaning that's an equal distribution. So what we're going to do for the time being is we're going to try to do the happy medium, whatever the phrase is. We're going to plan to have all Monday classes to be in person and all Wednesday classes to be online. We'll try that for the time being. If that turns out not to work, if that turns out to be messy, I will reassess whenever. But I will certainly reassess at the midterm, and we might do a new poll. We might get together again and say, all right, how's this going? Do y'all like what we're doing? Should we change it? But long story short, for the time being, all Monday classes will be in person. All Wednesday classes will be online until we feel the need to reassess. So, okay. So that's every class update I needed to mention. Are there any questions about that? Any questions about anything class related? Okay, not hearing anyone. So if you're trying to say something, unmute your microphone or just type in the chat window. Going once, going twice. All right, so no questions. So let's move into the lecture. So if there's no questions about the class, we'll move into the lecture. So first, I just want to start the lecture getting back into the mindset of statistics, getting back into the mindset of what we talked about on Monday. So I just want to give a quick chapter 1 statistical BS example. I said we're going to talk about it this semester, so we're going to talk about it. So one concept we talked about on Monday was this idea between measured variables and conceptual variables. How we're actually interested in the conceptual variables, where whenever we talk about research, whenever we talk about practice, we say things like job satisfaction. We say things like job performance, but we can't measure those directly. We don't have magical job satisfaction numbers above our heads. Instead, we have to get at a roundabout way to measure that. So this might be through a Likert scale, give people a survey on a scale from 1 to 6. Are you satisfied, dissatisfied, so on and so on. We could get monthly sales as an indicator of job performance. So we hope that whatever we're measuring actually represents that conceptual variable. We hope that. We can never, ever, ever know for sure, but we can collect some evidence and some support to say, all right, I think I'm doing a good job at gauging this conceptual variable. So that's one thing I wanted to note is, by the way, can y'all see my mouse on the screen? Or is okay, you can see my mouse? Oh, no? Okay, no, okay, so then I will try to, let's see if, okay. Draw, let's see. 1 sec, give me 1 sec. That's not working. Oh, I see what I'm doing, okay. All right, there we go. Let me change the color. Draw color to red, okay. So therefore, we always hope that our measured variables are representative of our conceptual variables. So therefore, we're hoping that this relationship is actually supported, but we can never know that for sure. We can never be 100% confident that our measured variables actually represent our conceptual variables, but we just hope for the best, and we do gather statistical evidence to support that relationship. Okay, so with that noted, clear all drawings. Okay. With that noted, there we go. So I want to give an example of statistical BS. So earlier in my consulting career, this was one of the first consulting gigs I did, is I did consulting work with a clothing company. They are a national clothing company. They are very popular. At the time, they were in most malls across America. I don't know if they still are. Malls aren't as big of a thing as they used to be, but at the time they were. So this clothing company, they wanted to measure the ideal employee. They wanted to make a new selection system. And they said, we have this idea of what the perfect employee is. And we want to make some type of selection system where people can take a survey and we'll automatically know you are the ideal employee. You are the perfect person and we want you to work for us. One thing that was weird about this survey is the survey was meant to select for productive employees, which is very common. It's very common for companies to want productive employees, but they also wanted hip and cool employees. That was like the main thing they wanted from the survey, because they said, people don't buy clothes from uncool people. They only buy clothes from cool people. So this survey was supposed to select for productive people and cool people. And also the survey had to be cool itself. They said, we don't want people applying for our position and getting these lame surveys because then they're not going to want to work for us. So instead, we want to get these cool surveys that people get all jazzed up when they apply for our jobs. Also, this was when millennial research was really big, and this company had very strong feelings about millennials and really wanted to capitalize on the millennial market. So that's what they were thinking. So this was an example question. The pictures are different because I didn't steal anything, but this was almost identical to what one of their questions on their survey was. They wanted to ask potential applicants, I guess, what are you more like? Are you more like a sports car or are you more like a Prius? So on a scale from -3 sports car to 3, are you more like a sports car or a Prius? All right, so question for the class, and I will expect y'all to speak up, so unmute if you want to talk. What's the problem with this? What do y'all see as a problem with this survey item?
What if you like trucks?
So that's a big one. Yeah, what if you like trucks? Who's to say trucks aren't cool? Who's to say trucks aren't hip? So you could be this third option that you would be the perfect employee, but if you like trucks, you don't know how to answer that. All right, what else is a concern with this question?
They mean different things to different people.
Okay, expand on that.
Like I might see that the Prius is new and inventive and like on the edge of everything that's current, and you might see a sports car as that way.
Exactly correct. And that was our biggest critique about this is believe it or not, the clothing company, they thought the Prius was the cool option. They were like, only lame people like sports cars, cool people like Priuses. They were very dead set on that. So if I can draw it right here. So when we were drawing this picture before with the 2 circles with conceptual variables up top and observed variables down below, not only do you have to make sure there's a relationship there, but you have to make sure that, I guess in this instance, that the conceptual variable you're wanting to measure, you actually have a firm definition for it. You actually have a firm concept for it. And that's one problem with this, is they had an observed variable, they had the survey, but it was very unclear what their survey was actually measuring, as they thought it measured this very clear concept of the ideal employee, but that was very different to everyone who took the survey. That was very different to everyone who saw the survey. So therefore, they made a survey and it was extremely unclear what they were measuring with it. It was very unclear. So that's one thing to remember about the relationship between observed variables and conceptual variables, is because conceptual variables are so abstract, you have to have a firm definition. You have to have a firm concept for those. And if your concept is something that's abstract of like, well, maybe people that like Priuses, since this was a clothing company, they had like clothing, they had articles of clothing from companies they thought were lame, and they had articles of clothing from companies they thought were cool. So they were like, oh, if you like leather jackets, you're cool. If you like V-neck shirts, you're not cool. It was so abstract. So even though they thought they had a conceptual variable, they didn't really know exactly what they were wanting to get at. So that was the first major concern with the survey. Okay, any questions about that so far? Okay. However, it was the next question that made us, and I was working on a team with this, made us say, no, you cannot use this survey under any circumstances. If you do, this is going to have terrible results. And it was this question right here. They had a question that was, on a scale from -3 to 3, how similar are you to Kanye West? So -3, you're not like Kanye at all, and +3, you are like Kanye. And I will say that they thought Kanye was really lame. So they were like, we don't want people who think they're like Kanye. We want people that are the anti-Kanye. All right, so what's a concern with that question? What would y'all think would be a concern with that?
What if you don't know who that is?
West is.
Sorry, I think there are two people talking. Try again.
What if they don't know who Kanye West is?
So that's one, yeah. So if you don't know who Kanye is, how are you going to answer that? What are you going to say? So many people might not know Kanye, and that kind of gets into the other big concern with it. So does anyone else want to say what a concern with this would be?
Like Kanye how?
I think someone's trying to speak. Your name's only iPhone, so whoever iPhone is, you can try again.
Like Kanye how?
Ooh, okay, expand on that.
Like him in celebrity, in appearance, in fame. There's just a lot of variables to that.
Exactly correct. So that's another big one. Is what do you mean by like Kanye? Like do you like his music? Do you like his politics? Do you like the way he looks? There's so many ways you can interpret that. So how the applicant perceived it would drastically change how they would answer it. All right. And any other concerns with this?
People could be wondering, like, if you say like him, like, okay, Kanye is African American. So am I supposed to pick him because I'm African American, even though my personality is not like him, or vice versa? So that could kind of be seen as, not really the best way to be rating someone.
100% correct. And that is exactly what we found. 100% correct. Is when we looked at the data, we saw that on average, Caucasians said they were not like Kanye that much at all, whereas African Americans were more likely to say that they were like Kanye. So we looked into that a little bit more, and we reached out to some of our Caucasian applicants, some of the African American applicants, and this never went live. This was all test examples. So we had people pretend they were applicants. And the Caucasian applicants said, well, Kanye, he has different background. He's African American. Sure, I like his music, but I don't really think I'm like Kanye that much. Whereas when we talked to our African American applicants, they said, oh, well, yeah, I like his music, but like, you asked me how much am I like Kanye? Like, I'm African American. I'm like him a decent amount. So therefore, just based on your race, you would have very different answers to this question. And in the context of selection, that has a huge impact. That has an incredible impact because they're seeing this as a negative. This company was, if they went live with this survey, you would have had points taken off if you said you were like Kanye. So just by seeing a picture of an African-American person and then saying, yeah, sure, I'm African-American, you would be penalized if this ever went live. So that's one thing to think about whenever you're thinking about selection surveys, because that's a huge issue. And that's called adverse impact. There's tons of research on adverse impact. It's an incredibly large field of study. And more, you would be surprised how often companies engage in adverse impact or have an adverse impact happen. Because they don't really think about these questions. They don't really think about these results. So in the context of statistics, when we're talking about observed variables and conceptual variables, you need to also think, do your observed variables measure something that's different than your intended conceptual variable? So in this example, they had a survey item and they thought it measured the ideal employee, but in actuality, this question measured race. This question measured race instead. So they were accidentally measuring a different conceptual variable. You might be able to argue, I guess, in some instances that maybe this question was more maybe like that, where it measured two things at once. It might partially have measured the ideal employee, but then also measured race. But even in that case, that would be a huge problem. That's called construct contamination. That's called construct contamination. That if you're thinking you're measuring only one thing, but you're actually partially measuring another thing too, that's also a huge concern. You only want to measure one thing with your observed variables. You only want to measure one thing with your observed variables. So in this example, they were accidentally also measuring race, and therefore they were going to have huge problems with their selection system. So we went back to them and said, no way, shape, or form should you ever make this live. Not only would it be unethical, but you're going to get sued. Like you would get sued so quick with that. So fortunately, the company said, yeah, you're right. We're going to scrap the whole system. And this was after they spent hundreds of thousands of dollars on it. They already paid a different company to come up with it. And then when we did our analysis, they said, yeah, you're right. We're going to scrap all that money we spent. And they started back at the beginning. So that's the thing I want to talk about with statistical BS is sometimes you think that you're measuring one thing, but in actuality, you're measuring the other. and that can be a huge concern. Okay, any questions about that or any comments about that? Okay, so let's keep on going. So now we're going to go into chapter 2. So that was our quick touching on a topic from chapter 1. So we'll move into chapter 2, and chapter 2 is about visualizing data. So looking at tables and figures. So chapter 2 is all about tables and figures. Okay. So in addition to methods and analysis, which we will talk about over and over and over this semester, the concept of statistics also heavily involves the presentation of results. You can be the best statistician in the world, and you can be terrible at presenting results and terrible at making your argument. And honestly, I see that quite often in industry. You'll see a lot of consulting companies that will hire people with, PhD in statistics. They could do any analysis you can imagine, but when it comes to actually selling their argument, they're terrible at it. They're awful at it. So therefore, it's really helpful to learn how to make figures, tables, charts, et cetera, so you can help make your arguments and show, all right, my analysis might have said the result was 2.167, but this is what it looks like. This is what we need to understand from that. All right, is this moving forward? 1 sec, sorry. There we go. Okay. Also, often to present the results of your analyses, so to make your tables, figures, and charts, you don't actually need to know the relevant statistics. So I know this sounds a little bit backwards, but that's why we're starting with this, is because to know the charts, you don't have to know what a t-test is, a correlation is, a regression is. You can start by making charts, and that's going to be really helpful going forward, because a lot of these charts do relate to particular analyses. So once we start learning those analyses, you'll instantly start thinking, oh, this data, I would make a bar chart, so that means I can do a t-test on it. Or this data, I would make a scatter plot to visualize it, so that means I could do a correlation. So understanding how you would visualize your data also is going to help you later on in understanding what analysis you should perform. Okay, and that's what that bullet point says. All right, so to start with this lecture, we're going to look at some of the graphs that should say current students. I think most of these are current. The graphs that I had y'all make and y'all submitted on Canvas. So I took some of those examples and we're going to go over them together as a class. So without knowing anything about the graphs, let's discuss whether these are good or bad. And just FYI, some of these are from prior semesters. So if you say something negative about a chart, it's probably about a prior semester, because I didn't take any that I didn't want anyone to feel bad. So don't feel bad saying something negative. All right, so this was the first one. So this was for database 1. This was the one where we had, I think it was 50 people applied for a job, and then they're hired, waitlisted, or rejected. So from y'all's opinion, just quickly, was this a good chart or a bad chart? Someone be courageous. Say what you're thinking. And you might have it on mute, so if you're trying to talk, I can't hear you.
It looks good.
Yeah, okay, so one person says it looks good. I saw some other people nod their head. Yeah, this is a good chart. I like this chart. So whoever made this one, good job. Give yourself a pat on the back. I want to highlight some things that are particularly good about this chart. So first off, every chart, every single time you make a chart, it needs to have a title. You need to have a title to your chart. So if you left that off of your chart, now you know. So this one has a title. The title, for me personally, I would be able to read it and know what database you're talking about. So that is relevant. But also if something wasn't familiar with the assignment, they could see that, oh, this is somehow the results of job interviews. And that's extremely important. Is when you're labeling your chart, you need to not only think, all right, if someone knows about what I'm doing, what do they need to know, such as labeling data set 1? But also if someone has no idea what I'm doing, has no idea what data set I was looking at, what information can I provide here that someone completely unfamiliar with the topic would be able to understand my chart? And that's one very important thing to think about when making charts, is what do I need to include on here that if someone has no idea what I did, if they only were shown this chart, I still want them to understand it. I still want them to understand the chart, even if they have no idea what I did before seeing the chart, that is. Okay, so the title, so good job on the title. Also, it's 3 different groups, and there were a number of people in each group, so good job deciding bar chart. This is a very good way to illustrate how many people are in each group. So also, good job labeling each bar. So whenever you make a bar chart, you need to label the bars. That's extremely important. So that way, if I had no idea what you were doing, I could just look at these bars and quickly understand, okay, this is job interviews. They had some people they hired, some people they waitlisted, and some people they rejected. So good job on doing that. And the last thing I want to note is they not only included numbers on the axis, but they also included numbers right here. So you can do one or the other or both. That either way is completely acceptable, but some way your reader needs to be able to quickly look at it and think, all right, so it's clear how many people are in each group. That you could look at here and say there's about 9, or just look here and say, okay, there's 9, 3, and then 38. So good job on labeling the bars. Good job for numbering your axes. I can look at this chart really quickly and within 10 seconds know it's job interviews. They hired, waitlisted, and rejected people, and most people were rejected. Some people were hired, and then some people were waitlisted. So very clear, very descriptive. Good job on that group. Okay, so let's move on to the next one. All right, so this was number 2. Is this a good, bad? What do y'all think about this chart?
I think the title could have probably been a little clearer. Just looking at the last one, if you just look and said job interviews, I mean, you would know kind of what they meant, but it's just not as clear. It's the only difference I really see.
So maybe this title could have been more descriptive. Yeah, maybe. It's up to the person, but yeah, it could be clearer. I see other people saying good. This one was kind of a trick question, I'll be honest, because this group I think made a small mistake, and that was, and I only caught this because I know the data. They accidentally switched the labels, so just be careful of that when you're making your charts. Is the data set actually had 38 people that were rejected and 3 people that were waitlisted. So just be careful of that type of thing. So everything else about it was perfect, had clear descriptions. Yeah, maybe the title could be more descriptive, but overall it was fine. And good job, you included the labels, just had these groups switched. So very small mistake. Okay, next one. Okay, so this is the same data set, but this group made a pie chart. Was a pie chart acceptable for this? What do y'all think?
Yeah.
No, because you can't tell the total as
So some
easily.
people said yes, some people said no because you can't see the total. So
I say yes.
okay,
It just
another
depends
person.
on how you want to view the data. If you want to look at percentage rather than value.
Okay, yeah, so maybe percentage rather than value. So some people say yes, some people say no. I think this is fine, to be honest. I think this is fine. Yeah, they could have put percentages here instead of the raw numbers, but you could put the raw numbers. That's really preference. But they had a good title. They had it clearly labeled, and they had the numbers here. That's really up to you. One thing about pie charts that's useful is just by the nature of the pie chart, you can get a rough approximation of the percentage. So just by looking at this, we can roughly approximate that about 75% were rejected, maybe about 20% were hired, and then maybe about 5% were waitlisted. So that is a good thing about a pie chart, is just by looking at the distribution of the colors, we can see rough approximation of percentages. So I was fine with this one. One thing to note, and we'll talk about this later, is that even though it's the same data set, multiple different types of charts could be acceptable. So even though both of these examples use the same data set, both a bar chart and a pie chart could be acceptable. So keep that in mind as we go through the semester. All right, next one. This is an example, and I'll just give the answer to this one. So I thought this was also appropriate. This is once again a pie chart. Once again, the same data set. The only thing I would say to change about this is if you're going to use percentages on your charts, make sure you include the percentage symbol after the number. Because most people, when they see charts, they typically tend to think, all right, this is the number of raw values. So they're saying that 76 people got rejected, 18 got hired, and 6 got waitlisted. But instead, this group was wanting to show percentage. And even though they had it in the title, which is very good, this is a perfect title. So give yourself a pat on the back for that. They did need to include those percentage signs. So once again, if you're going to use percentages, make sure you use those percentage signs. Okay, so clear all of that and then move forward. And that's what this group did. So once again, this group had a good title. They used percentages. They had a pie chart. So good job to that group. So what I wanted to see. All right. So this was data set number 2. So this was factories, looking at differences in performance across the factories. So do y'all think this was a good example, bad example? What would y'all improve about it? What do y'all think?
Too many decimal places.
Okay, yeah, so that would be one change is, yeah, you probably don't need all of these decimal places. Good job including the number. The number is very good. The number is very important. So give yourself a pat on the back for including the number. But you could go with fewer decimal places, and you probably should go with fewer decimal places. Particularly in this example, I think all the numbers were integers. So the numbers went from like 1 to 10 and they weren't decimals. So probably all of these decimals aren't going to be that important in providing these results. I see someone in the chat saying that training is misspelled in the title. So yeah, make sure you do typo checks. So make sure you spell everything correctly. That is something difficult with Excel as it does not have autocorrect on that. So make sure you're spelling everything correctly. But yeah, I think those were the 2 things I wanted to point out about that. I thought this group did a good job labeling factory, and then we know it's 1, 2, 3, and 4. They did a good job at labeling this as average rating, and therefore we can know the average rating. And I also appreciated that they included the numbers. They could go with fewer decimal places, but the numbers were good to include. So good job for that group, just some small changes. Okay. Next one, this is a different data set. So this was data set 3. So what do y'all think of this chart? So if you didn't look at data set 3, what would y'all think this chart is telling you?
We don't know, there's no labels.
Sorry, say it again.
We don't know, there's no labels.
Exactly correct. You don't know because there's no label. You know that there's somehow totals. You know that we have somehow 1, 2, 3, 4, and 5. But yeah, there's no labels on it. So this was from a prior semester. This was not in this semester, but I still wanted to include it because you can see it's general and normal distribution, but you have no idea what they're talking about. You have no idea what they're looking at. So once again, going back to this idea that whenever you make a chart, if someone's completely unfamiliar with your data, they should still be able to understand generally what you're talking about. They should be able to get a general impression. And in this example, you can't get an impression of what they're talking about. You have no idea what they're talking about. Okay, so clear that. Here's another one with the same data set. So one much better is now you can see, oh, it's a job satisfaction survey. We're talking about the results of a job satisfaction survey. This group, and this was from this semester, so good job to this group who did this. So know it's job satisfaction. You see this as a rating of satisfaction. So you know it's from 1, 2, 3, 4, and 5. And then also you see this is the count of responses. This is the number of responses for each group. There's only one thing that I would possibly add to this, and they might have included it in the Word document, but maybe try to include it somewhere on here, is whether 1 is bad or whether 5 is good, something like that. So maybe include, 1 strongly disagree, and then 5 strongly agree. Just some type of indicator of, well, which one of these responses is the good one, and which one of these is the bad one. Because when you're looking at this, you see it's a normal distribution. You see slightly more on this side, but you don't know if that's good or bad. You don't know if that's good or bad. So somehow including that type of indicator would be helpful for this chart. But everything else about it, very good. So good job to that group if that was you. Okay. And then here's another example. I just wanted to show that, yeah, you could include percentages. So bar charts, you could have the count values, you could have the raw values, but bar charts, you can also include the percentages. Completely up to you, however you want to go about it. It should depend on what you think is more important for your reader to know. Does your reader need to know the raw value, the count values, or does your reader need to know the percentages? That's going to be up to you, and it depends on your research question. Okay, clear all that. And then, yeah, so once again, same thing, using percentages. The main thing I wanted to show about this one is they did include the response format. So here, very quickly, you could see this is job satisfaction. It's a general normal distribution, but there are more on this side, and that's a bad thing because we see that down here means that people are dissatisfied. And because we have slightly more people that are dissatisfied, we probably want to do something about that. So once again, labeling as much as possible so someone who's not familiar with your data set can understand what's going on. Okay. So that is all for that one. So this was data set number 3, I believe, or are we on 4? It's either 3 or 4. This was the only one group made a chart of this data set, and I think this was the hardest data set to make a chart for. So open up to the class. Is this a good chart for this data set?
Yes.
Yeah, so I thought this was a pretty good one. I was very appreciative that they chose a line chart. So this group chose a line chart. The reason why this was extremely important to choose a line chart was because these were multiple factories and their performance across time. So these are the same factories and their performance across time. And we'll talk about this a little bit more later. But whenever you have something that goes across time, so something like factory 1, 2, 3, and 4, at time point 1, 2, 3, and 4, you need to show that these are the same factories over time. You need to show the progression of the factories over time. So for example, we have factory 1, which is blue. So looking at this very quickly, we can see, oh, this blue factory, they stay pretty low the entire time. They do a pretty bad job the entire time. And because we made it a line chart, we can see that progression very easily. So good job to this group for doing that. You did a good job at choosing a line chart. So also just from this really briefly, we can quickly see that factory 1 did pretty poor the entire time. Factory 2, which is orange, improved consistently. So factory 2 was the one that started off poor but got better. So whoever's the manager at that factory, we need to promote. We then see factory 3, which is gray, also was poor the entire time. So factory 3, which is gray, also did a poor job the entire time. So factory 1 and factory 3 are the ones we need to watch out for. And then also because it's a line chart and we can see these progressions, we see that factory 4 was pretty good the entire time. Factory 4 did a pretty good job the entire time. So because this group made a line chart and they did a very good job at it, we can very quickly see that factory 1 and 3 are problem factories, whereas factory 2 and 4 are the good ones. 2 got better as time went on, and factory 4 stayed good the entire time. So therefore, whenever you think of a line chart, you should think, oh, I'm trying to show something as it progresses across time, as it changes across time. And this group did a wonderful job demonstrating that. Okay. And then this was I think this was the last data set. So this was looking at the relationship between job satisfaction and job performance. So this covers pretty much everything we've already talked about. They had a good title. So good job to that group for having a good title. Whenever you're wanting to show something that's the relationship between two variables, and they're both continuous variables, such as job performance and job satisfaction, you're going to want to do a scatter plot. So this chart is a scatter plot. It's showing the relationship between two continuous or semi-continuous variables. These variables are more semi-continuous. We'll ignore that. But if you ever want to do a relationship between two continuous variables, you're going to want to do a scatter plot. So good job for this group for identifying that. So this group, they plotted all the observations, where in this example, you can see that right here, they had a job performance score of 1, and they had a job satisfaction score of 1. And then right here, you can see this plot right here. This person had a job performance score of 2, job satisfaction of 1, and so on and so on. We can pick any point and instantly know what that corresponds to, such as this one up here, job performance score of 4, job satisfaction score of 5. The other important thing about a scatter plot is that you probably usually always want to include a line of best fit. And this is what this line is right here. This is your line of best fit. And what that does is it includes the line that best describes the data. It includes your line that best describes your data. One way to think about it is it draws the line that is the closest to all of your data points. So this line of best fit is the line that is closest to all of your data points. But if you were to draw any other line on this chart, it would not fit your data points as well. This is conceptually similar to a correlation. So later in the semester, once we get into correlation, you just need to think of that as, oh, it's the line of best fit. That a correlation and a line of best fit go hand in hand, and it's the line that best describes your data. So just from looking at this, we can, in our line of best fit, we can generally know that, oh, there's a positive relation between job performance and job satisfaction. That as job performance goes up, job satisfaction also goes up. And we get that from the line of best fit. Okay. So I think that was the last one. Yeah. So therefore, in summary, a good graph should easily explain some result or phenomenon without needing additional information. And that's the thing we kept on coming back to in those examples, is y'all did a very good job. Y'all seem you already know how to make charts, you already know how to make graphs, but to put some words on that of why y'all succeeded with that, is that you were able to make charts and graphs that were understandable without additional information. That for most of them, we could look at it instantly and think, okay, I know what they're trying to say. And that's the sign of a good graph. Also, however, additional information is almost always required to ensure that the inferences are valid. And that's what we're going to learn later throughout the semester. Is we're going to start with us making charts. And then as we progress, it's going to be, well, how can we supplement these with statistics to support our argument? Because a chart is never enough. A chart's not going to be enough to make your argument. A chart can display your argument, but you're going to need those cold, hard numbers to say, all right, my result's statistically significant, therefore my chart works. My chart is valid. Okay. And then continuing. All right. So then now we're going to discuss some common graphs and when to use them. So we're going to talk about some of the types of graphs we just discussed. But before we do that, are there any questions or comments about anything? Any questions or comments about the charts we just looked at? Okay. So let's continue. All right, so the first one we're going to talk about is actually a frequency distribution table. So none of the groups made this type of table, so this is a new concept. So a frequency distribution table is used to show the number of responses or assignments in given categories or ranges. So you're going to make a frequency distribution table when you have a grouping variable and you're wanting to show how many people are in each group. So a frequency distribution table is when you have a grouping variable and you're wanting to show how many people are in each group. So your data set might have gender, and you might have people who gave responses of male, female, or other, and you might have 10 male, 10 female, and something like 10 other. So therefore, you can make a frequency distribution table to visualize how many people are in each of those groups, 10, 10, and 10. And we'll see an example in the next slide. So this is useful for questions like how many people gave a certain response to a survey, such as male, female, other, to the question of gender. And it is also important for displaying the demographic information for a sample. So what's your sample composed of? You can have a frequency distribution table for gender. You can even do it for age, ethnicity, so on and so on. It's a very quick, easy way to show demographic information. There we go. It's most often used to visualize a single categorical variable. So typically when we're wanting to show the results of a single categorical variable, we're thinking of frequency distribution tables. If you have more than one categorical variable, or if you have a continuous variable, you're probably going to be thinking of a different type of chart, but frequency distribution tables are for one categorical variable. And also there's two types of frequency distribution tables. The first type is a frequency distribution table, and the second type is a relative frequency distribution table. The only difference between these two is a frequency distribution table just provides the raw number of observations. So if it's male, female, gender, it might, or sorry, male, female, other, it might be 10 male, 10 female, 10 other. So you just give the raw values. Whereas a relative frequency distribution table gives the percentages. A relative frequency distribution table gives the percentages. So it might be 33% male, 33% female, 33% other. Okay, and here is two visual examples of frequency distribution tables. So as you'll see on the left, with the hire, reject, wait list, that is a frequency distribution table. We had 4 that got hired, 32 that got rejected, and 4 that got waitlisted. So in this example, we have a single categorical variable, the decision of the applicant, and then we have how many times do we make that decision. So the number of observations for a single categorical variable. All right, on the right-hand side, we have a relative frequency distribution table. And as you can see, the only difference is we're talking about percentages here. We once again have a single categorical variable with the options of hire, reject, or wait list. And then we just have percentages there. So 10%, 80%, and 10% again. So that's pretty much all there is to know about frequency distribution tables. That's how they're made. If we wanted to make it with any other variable such as gender, we would just replace the decision with gender, and we would have male, female, other as the options. And then we would just put how many people fell into each response category next to the respective gender. So any questions about that one? Okay, so let's continue. All right. The next one is pie charts. It seems like y'all already understand pretty well when and how to use pie charts, but pie charts are typically used to show percentages of responses in given categories or ranges. As we saw before, you could use it to show the raw number of observations if you include the numbers, but it's typically used to show percentages. So the one person in chat that said pie charts are better for percentages, that's typically when they're used. So good job for you. It largely has the same function as a relative frequency distribution table. So in that last example, whenever you thought, oh, maybe I could use a relative frequency distribution table for this, you could also use a pie chart, because pie charts are used to show the percentage of observations for, the percentage of observations for the different options of a categorical variable. So pie charts are used to look at the percentage of responses for a categorical variable. So once again, looking at a single categorical variable and the percentage of responses. Okay, once again, here's an easy example. We have hire, reject, wait list. We see most people were rejected, some people were hired, and some people were waitlisted. Of course, this pie chart could be improved upon. We might want to include the numbers with the percentages, something like 80%, 10%, if I could draw better, and then 10% would be an improvement on that, but y'all get the idea that a pie chart shows the relative percentages, and just due to the nature of the pie chart itself, you can get a pretty good idea of what those percentages are. Okay. The next one, stem and leaf plot. To be 100% honest, our book covers this. It's very rare I ever see anyone use a stem and leaf plot. Most business statistics textbooks don't really talk about stem and leaf plots, so therefore I'm not going to make you learn it. So for those who listen to this lecture today, good job. You now know something that's not going to be on the test. Don't look at stem and leaf plots. Those who skip this lecture, study the stem and leaf plots and then find out it's not on the test. So we are moving on with that one. Don't study stem and leaf plots. Okay, so the next one is bar chart. So bar charts are most often used to show the differences between groups on a certain outcome. So bar charts might be used to visualize questions like, which training group had the best post-training performance? Or which factory is performing the best? Or something like, which tax rate of the what is the tax rate of the 20 lowest rate states? So in all of these examples, we have some type of outcome variable, such as post-training performance. That's an outcome variable. Which factory is performing the best? Performing is an outcome variable. In the last one, what is the tax rate of the 20 lowest states? Tax rate in this example is the outcome variable. So whenever you're making a bar chart, you're going to have an outcome variable, but you're also going to have a categorical variable. So in this example, the categorical variables are in these examples, the categorical variables are training group for the first one. So which training group is the categorical variable or the grouping variable? For the second one, it's which factory. So the factory or which factory is the grouping variable. And then for the very last one, the grouping variable is the state. The grouping variable is the state. So you're going to make a bar chart when you have a grouping variable and when you have an outcome variable. So you're going to have two different variables, and you're wanting to visualize the difference between those groups of the grouping variable. So whether it's different training groups wanting to look at the differences in their performance, whether it's factory and wanting to look at the differences in their performance, or whether it's states and wanting to look at the differences in their tax rate. In all these examples, we have a grouping variable and we have an outcome variable. Okay, and once again, it's typically used for making comparisons. So we need a grouping variable and we need an outcome variable. So this is a very simple example of a bar chart, very, very simple example. So in this, we see the grouping variable as class. So we can very quickly see the grouping variable as class, and we have class 1, 2, 3, and 4. So our categorical variable was class, and we actually don't have the outcome variable labeled. So it could be anything, but we see that it goes from the lowest one being, what is that? That's a 70, to the highest being a 90. So let's assume this is something like test scores. Let's assume this is something like test scores. So we have our grouping variable of class, and we have an outcome variable of test. So in this example, our grouping is class, outcome of test, and we can very quickly see class 4 did the worst, class 2 did the best, and then class 1 and 3 did somewhere in the middle. Class 1 and 3 did somewhere in the middle. So very quickly from looking at this bar chart, we could see whoever's teaching class 4, we need to talk to that person. And whoever's teaching class 2, we need to thank them, give them a pay raise, do something beneficial for that person. So therefore, once again, bar chart is used to visualize the differences in the groups of a grouping variable regarding some type of outcome. That's when you're using a bar chart. Okay. Also, a special type of bar chart is a histogram. So a histogram is a special type of bar chart, and a histogram is used to show the distribution of data. So that was I think it was data set 3, where you had a single variable of job satisfaction, and you could visualize what the distribution of responses on job satisfaction was. So groups who did that, you made a histogram. You might not have known it was called a histogram, but that's what you did. So there are 4 questions that could be answered with the histogram. Is what's the distribution of job satisfaction in a sample, or something like what's the distribution of production in a sample of factories. So you're making a histogram when you're wanting to see the distribution of a single variable. Typically, it's going to be a continuous variable or semi-continuous. Theoretically, it could be categorical, but typically you want it to be continuous or semi-continuous. But either way, it's going to be one measured variable. Either way, it's going to be one measured variable. So in this example, we have one measured variable, and that is the question, rate the extent you disagree or agree with the following statement. I am satisfied with my job. And therefore, you then just plot how many people said strongly disagree, how many said agree, how many said slightly, and so on and so on. So a histogram is just plotting the number of people that gave each response to a single question. A histogram is just plotting how many people said each response to a single question. And like I said, it's a special case of a bar chart. So in this example, we can see that the answers to this question, I am satisfied with my current job, is a completely normal distribution. It's a completely normal distribution. I'll say with me personally, this is the chart I make most often because whenever we're doing analyses, one of the assumptions we'll talk about later in the semester is whether our data is normal. We like to assume our data is normal, but that's not always the case. So one way to very quickly get a rough estimate if your data is normal is just to make a histogram. It's just to make a histogram. And if your histogram has a rough bell curve shape, then that supports it is normal. So in this example, if I was using this question for research purposes and I made this histogram and I saw the question look like this, I'd be very happy about that. I would be able to say, oh, look, it's pretty normal. Yes, I would go ahead and calculate my statistics for normality, but I would off the bat know, all right, that looks normal. It's probably going to be normal. I'm not going to have to do any type of adjustments with my analyses. I'm going to be happy about this. So histograms are very, very important, no matter how basic or how complex you're going to do with your analyses. Okay. And then also line chart. I think this is maybe one more after this, but we have a line chart. And as I mentioned before, line charts are most often used to show how trends and differences occur over time. It's used to visualize trends and differences over time. Time being the important thing here. So questions you might be able to answer or look at with a line chart is how well has a factory or factories performed over time. And that was the example we showed with, I think, data set number 4, where that one group made the really, really great line chart. They were looking at how factories performed over time. Another example of a line chart is one y'all have seen many, many, many times before, is what is the change in stock value over time. So when you're looking at the stock market, that's just a basic line chart. And that's because they're looking at how a single stock has changed over time. So once again, looking at how to visualize changes in something over time. And that's why stock is most often represented with a line chart. So typically when we have data collected at multiple time points, so whenever we have longitudinal data, we probably want to think about a line chart. Whenever we have longitudinal data, we probably want to think about a line chart. So whenever we have a variable, no matter what it is, that's been measured multiple times, we probably are thinking line chart. Not always, but that's a good place to at least start at. Okay. So once again, an example, this is pretty much the same as we looked at before. We have company A, B, and C, and we see that this is their revenue over time. We have quarter 1, quarter 2, quarter 3, and quarter 4. And because this is a line chart, because we know this is over time, we can quickly see that company A got a little bit better over time. Company B got a lot better over time, whereas company C got worse over time. So once again, visualizing those differences over time. Okay. Oops, need to clear that. Oh yeah, I think this is the last one. Is a scatter plot. So a scatter plot, like we looked at before, is used to show the relationship between 2 or more variables. So if we were ever thinking about how are things interrelated, so how are 2 particularly continuous variables interrelated, we're going to be thinking about scatter plot. So questions like what's the relationship? So thinking about interrelatedness. So what is the relationship between job satisfaction and job performance? That's a question for a scatter plot. That's something that could be visualized with a scatter plot because we're looking at the relationship between 2 variables. Another example is what's the relationship between factory size and production? Once again, 2 variables that are continuous or semi-continuous, and we're looking at their relationship. So relationships with 2 variables, usually things that are going to be continuous or semi-continuous, not 100% always the case, but usually things that are continuous or semi-continuous. Okay. So here's an example of a scatter plot. As we see, we have job performance and job satisfaction. So job performance on one axis, job satisfaction on the other. And like we saw before, we can look at each of these plots and quickly see, all right, so this represents one individual. This individual had job performance score of 60 and a job satisfaction score of 10. This person right here, job performance score of 70, job satisfaction score of 30. There is one thing missing from this scatter plot. What's the thing that's missing? Yep, that's it. I saw 2 people do this motion, so yeah, good job. We're missing the line of best fit. So if this scatter plot wanted to be even better, we would tell Excel to include the line of best fit, which is pretty much a regression line or a correlation line, and it would probably look something like that. So we would very quickly know there's a very strong and a very positive relationship between job performance and job satisfaction because this line goes up like this. And that is something we'll cover more in depth later in the semester. But this is a scatter plot looking at the relationship between 2 variables and looking at their interrelationship. Okay. All right. So that's all the examples of charts. So let me say this really quickly. Is most often statistics involves taking something that we think, often through visualization, and finding out whether it's actually true. So very often in statistics, whether you visualize it this way or not, you'll have something that you think is true. A lot of people might visually think, all right, if I were to compare these groups, it would look something like a bar chart, and the bars are going to be a lot of different heights. I think there's some difference there. So we often take what we think or what we see through data visualization and finding out whether it's actually true through conducting statistics, whether it's a t-test, ANOVA, correlation, regression, so on and so on. So therefore, it's very important to understand data visualization, to become good at it, because that's often where we start. That's often where we get our ideas from. Whether we consciously think of it that way or not, that's a whole nother question. But often we think about our data through data visualization before we move on to actually finding out whether it's true with statistics. Here's an example of that. So we have multiple time points. So this is a single factory over time. So in this example, the factory has millions of dollars in revenue. So this is one factory over time and looking at their revenue in millions of dollars. And we see there's an intervention done at time 2, and it was taken away at time 5. So an intervention was done at time 2, such as hiring a new manager, and it was taken away at time 5, such as firing that manager. So just based on this, what would y'all think the results of this study would say? What are the inferences you can take from this study?
Intervention was effective.
Exactly correct, 100% correct. That we see that, that it was pretty flat right here. We did an intervention and it skyrocketed. And then when we took that intervention away, it went all the way down. It went back down. So just from data visualization, we can get a pretty good feel for, well, what do we want to look at? What do we want to show? What are the results? And then we can go on to using statistics to support those inferences. We can then go conduct those analyses to verify what we think. But it's very important first to visualize our data so we can get a good idea of, well, what do we want to show? What do we want to support? And that's why we need to think about data visualization thoroughly when we're thinking about statistics. Because sometimes we'll have examples like this, where, and this honestly is how most real world data works. If you're working in a business, if you're looking at their data, this is how most data looks, is it's much more ambiguous. It's much more ambiguous. That we'll have, all right, so things were pretty flat. We did an intervention, things got a little bit better, but not that great. They stayed pretty constant. And then when we took the intervention away, yeah, it went down a little bit, but then it went back up. And you might not know how to think about things just based on visualization. So just based on visualization, you might, well, things might look sort of okay, but not great. And that's why we need to do the analyses. That's why we need to learn statistics. Because more often than not in the business world, more often than not when you're working with real world data, your data is going to look like this. Your data is going to function like this, where things might sort of look okay, but not be great. And you need statistics to know, well, is this a valid result or is it not? Is this statistically significant or is it not? But this still frames the way we think. Okay. So once again, in short, without statistics, we couldn't be certain of observed effects in many instances, but a good graph is meant to present information visually without needing to explain it with other information. That a good graph should be able to express your thoughts, or a good chart should be able to express what you're thinking without needing additional information, but that additional information is necessary to fully support your results, to fully support your argument. Okay, so are there any questions about that? Any comments about that? Any questions or comments about anything we covered? Okay, so let's look at this quick thing real quick, and then we'll go on a break. So this happened, I think, 3 years ago now. So this was a chart that I made with data that came up at the time. So first off, without knowing anything else about the chart, what's something you can infer from this chart? What's something that you can tell from those lines? Any guesses? How about the relationship between those two things? Can you infer any relationships between those two things?
They occurred at the same time.
Okay, so first off, they occurred at the same time, so good job. As we have time down here. So they occurred at the same time, so we know they occurred at the same time. Is there anything else we can say about it, particularly with this section right here? So we know they occurred at the same time. Is there anything we can say about that right there?
They hit a peak within 30 minutes of time frame.
Okay, yeah, so they hit a peak within 30 minutes. So when blue hit its peak, then the other thing hit its peak 30 minutes later. And that's pretty much what I was wanting to get at. That just from looking at this data visualization, knowing nothing else, we can infer that there might be a causal relationship between these two things. There might be a causal relationship. That the blue line hit its peak, and then the orange line kept on getting higher until it hit its peak, and the blue line dropped as the orange line got higher. So there might be a causal relationship between those two. because when blue hit its peak, orange hit its peak, and when blue went down, orange went up. So then to show a little bit more information, once again, this was from 3 years ago. What this data was this was Google search trends. So this is when people searched on a certain day for solar eclipse. So this is when the solar eclipse happened 3 years ago. And this was how often people searched Google for the word solar eclipse. So that was the blue line. And believe it or not, I am not making this up. The orange line was the Google search for my eyes hurt. Believe it or not, yep. So as you see, the solar eclipse happened. What's that, about 4:40 or so? And then within 30 minutes, people started searching my eyes hurt. Because of course people went, looked at the solar eclipse without glasses, and then that became the most searched thing on Google for that brief period of time. So therefore, a good graph without knowing anything else, if I was just to show you this, you could understand, oh, this is solar eclipse, my eyes hurt, Google Trends, and there's some type of causal relationship. The people looked at the solar eclipse, and that made their eyes hurt. The other thing you can know from this graph is that people can be really, really dumb. So graphs can be extremely informative in that regard too. All right, so let's go ahead and let's take a, what time is it? It is 7:06. Let's go ahead and take our break, if that's all right with y'all. So let's take about let's do a 9-minute break, and let's meet back at 7:15. So let's take a 9-minute break, and let's meet back at 7:15. So I'll see y'all in 9 minutes. Okay, so it is now 7:16, so let's go ahead and get started again. Are we good to go? Good, very good. Okay, so to continue, I just want to wrap up the discussion of graphs and charts. Particularly, I want to talk about statistical BS again, and I want to go over a quick demonstration of how badly can you lie with charts. This is probably the most common and the easiest form of statistical BS. Like I said, whenever I do consulting work, I feel like I always see other people, they throw up a chart for 30 seconds and then take it down and just, expect you to ignore everything that was wrong with it. So it's good to see some examples. So maybe we could catch these things in the future. So here is the first one. Can anyone tell me what's wrong with this chart?
It doesn't add up to
It doesn't
100%.
equal 100. Yeah.
Yeah. So the first one is it doesn't equal 100. So it's 50 and 49. So, all right. So definitely some question there. What's the other concern with this chart?
50% should be more than 49.
Sorry, say it again, but louder.
50% should be more than 49.
Yeah, so the distribution of these colors are completely wrong. That it should be something more like that, but instead they shaded it completely incorrectly. So that is one easy way to lie with a pie chart, is hope that your participant or your viewer doesn't read the numbers quick enough, and instead they just look at the shaded area and assume, all right, so no must have been the more popular one. So that's one way to lie with charts. Here is another one. I don't even know if this is lying or if this is just a bad chart. As you can see, it's a pie chart, and I believe this was, people's opinions of the three people who were GOP candidates at the time. The obvious concern here is this adds up to way more than 100. I believe what the problem here was that they should have made a bar chart. I think these were independent questions, and it was, do you like Huckabee? Do you like Romney? Do you like Palin? And all of them were yes or no. And they tried to throw them all into a pie chart. So that's another form of statistical BS. It's just not knowing what you're doing and just, trying to force it into a pie chart when it's clearly not appropriate, because this adds up to way more than 100. Okay, here is another example. This is one of my favorite. So the question was, apparently Americans who have tried marijuana, and the options, once again, add up to way more than 100, but the options were 51% today, 43% last year, and 34% 1997. So I have no idea what was happening in 1997, but that must have been a good year. But as you can see, once again, very inappropriate use of a pie chart. So wrong that I don't even know what they were trying to say with this. I can't even begin to guess what they were trying to say. So once again, your chart should be clearly labeled, but also use the appropriate type of chart. Oh yeah, another example. So what's the problem with this chart? So can anyone tell me what the problem with this chart is?
The bars in comparison to the percentages are way off.
Exactly, 100% correct. Once again, the bars should be about the height of the percentages, but as you can see, they're way off. Is that we have 34, 28, and 25 that are the lowest, and then for some reason we have 13 that's the highest. So once again, if you want to lie with charts, show your question, show the responses, and then just make the response you want people to think was most popular the highest, even if your data says the exact opposite. So very easy to lie with charts. Here's another example. This is one of my personal favorites. It's from a research article. This was in an actual academic paper where someone did actually a really good study. It was a very well-made study. And they're trying to show the results of their analyses. But yeah, whoever said that in the chat, Nicole, way too busy, way too busy. When I got to this in the article, I literally just shut my window. I was like, no, I'm done with it. I don't even know what they're trying to say. And I later opened it back up and I read the text, and it included things like, as obvious from our chart, and there's nothing that's obvious about this chart. There's nothing you can get from this chart. So remember that when you're making your charts, is your charts can be way too busy. And if your chart is way too busy, there's no way for your reader to understand anything you're trying to say. I show this chart every year that I've been teaching, and I still have not figured it out. I still don't know what they were supposed to say with this. All right, here's another example. Once again, just bad labeling, very unclear. The question was, who has the world's strongest economy? So we have different countries, but then the two different things in each country was either the United States or China. So once again, very unclear. Were these the response options? Was it United States and China being polled, and the different response options were these? Very unclear, very hard to tell. So once again, need to make your chart clearly labeled. Once again, another one of my favorites. This one's more difficult to tell what's wrong with it, but can anyone see what's confusing about this chart?
There's no 0 point on the.
I see why you would say that. It does have a 0 point, but what's confusing about it?
It's upside down, is it not?
Exactly correct. 100%. Yep. And good job to Zane Patterson. Yep. 0 is on the top and it's flipped upside down. So this was in a publication that was wanting to argue that the stand your ground law, and once again, I'm not saying this to be political, but this is just the data in 2005. This publication wanted to try to argue that the stand your ground law reduced murders committed using firearms. But as you see, when you look at it, all right, murders, they were high, that law was enacted, they look like they dropped. However, the chart's upside down. The y-axis is upside down. So actually what happened was murders were already decreasing, they stayed flat, and then when the law was enacted, they then increased before rebounding a little bit. So once again, if you want to allow with numbers, if you want to allow statistics and they don't support what you're saying, just flip your chart upside down. Apparently that works. And that's what this person did. And then next one, oh yeah, this is the last series of ones. So this was baseball broadcast on TV. They had the pitcher R.A. Dickey. So they wanted to show how often he throws a knuckleball, how often he throws a fastball. And once again, the chart's very different numbers. However, they made the bars very similar heights. But at first look, you would think, oh, he throws a knuckleball maybe 60% of the time, fastball maybe 40%, when in reality it was closer to 90% and 10%. Then later I also saw this graph where once again, R.A. Dickey talking about his knuckleball, 75 miles per hour in 2013, 77 in 2012, but they made the bars so different you would think that 2013 was only half as fast as 2012, when in actuality it was only 2 miles per hour different. So once again, making very different bar heights, even though the numbers were very similar. So something to watch out for, that if you see someone who has very different bar heights, make sure that the numbers are actually very different and they're not just trying to sway you with their numbers. So after finding these bar charts about R.A. Dickey, I found out that there at one point was a website, it doesn't exist anymore, that was just dedicated to making charts about R.A. Dickey's knuckleball. I don't know why this existed. I don't know why anyone would do that. But there was a website where it was just collections of people making charts about his knuckleball velocity. So once again, silly chart, it's miles per hour. They made it with pie chart, doesn't make sense, so don't do that. One of the examples that someone made on the website was a flow chart for R.A. Dickey's knuckleball. So did he start? Did he throw a knuckleball? Is it 2012 or 13? Miles per hour? I have no idea why someone spent their time on this, but people really were into R.A. Dickey's knuckleball at the time. So the summary of this is that often detecting BS in graphs is just as important as knowing how to make good graphs, that it's so easy to mislead with graphs. It's so easy to mislead people with graphs, especially in business. I've seen people make terrible business decisions just because they didn't understand how to read a graph. Also, the other lesson is apparently really hard to make a graph about R.A. Dickey's knuckleball velocity. So if you're an expert on that, contact ESPN, maybe they need you. Okay. So therefore, chapter 2 review, make sure you understand when and why to use each visual presentation method. So that's one thing you should take away from this, as we talked about, do you have a continuous variable? Do you have a categorical variable? Is it one variable? Is it two variable? Make sure you know when and why you would make each type of chart. Also, one important thing to note about that is I know people who work in statistical consulting firms that literally make a living making charts and figures. I have a friend who got his PhD in industrial organizational psychology. He can do any stat you can imagine. He is a stats wizard. He has literally invented statistics, and he spends his entire day, all day, making charts. That's the only thing he does. And he gets paid a lot for it. He gets paid a ton for it. He might make maybe as much as twice as much as I do just to make charts all day. So it's one of the most important statistics related abilities to have, that if you can clearly make an argument with numbers, with charts, business people like that. Business people appreciate that. So that is a good skill to have. Okay, any questions about chapter 2? We are now done with chapter 2. Are there any questions about it? Okay, so let's go ahead and move on to chapter 3. So chapter 3, we're going to cover descriptive statistics. So question of the class, what are descriptive statistics? What are descriptive statistics from Monday? What do they do?
They describe data.
Yeah, there you go. They describe your data. They describe your data. So descriptive statistics are meant to describe your data, not necessarily to draw inferences about relationships, but instead just describes the shape of your data. It describes the form of your data. So the first question is, why is this important? So first off, most inferential statistics are built on descriptive statistics. So to understand the analyses we're going to do later in the semester and the analyses that could make you the big bucks, you have to understand descriptive statistics, because those more complicated analyses are built upon these more simple analyses. Also, it can help us understand our sample. It can help us understand our sample. So for example, if someone tells you the average tenure of our sample of employees is 5.4 years with a standard deviation of 4.7, once you understand these concepts, you'll very quickly be able to understand, okay, well, that's relatively short tenure, but we do have some people with longer tenure than 5.4 years. So that's pretty typical for a company. At the same time, descriptive statistics can help you identify whether something weird is going on with your sample or data, whether there's something problematic going on with your sample or data. So for instance, if you calculated the average of tenure in your sample, if you have a sample of employees and you got the average tenure and it's 107, you should instantly know, all right, there's something wrong with my data. There's a mistake with my data. I need to go fix that. One thing that's really common with that, and this is more of an aside, is a lot of old statistics programs to impute missing data, to tell the program you have missing data, you would have to type in 99999, or maybe just 4 nines. And some programs still do that. Some old school statisticians still do that. So often when you calculate, average tenure for your sample, if you're getting your data set from someone else and you get a crazy number like that, like 100, it's probably because they left in 9999 for missing data. Very, very common. But you have to know statistics. You have to know descriptive statistics to be able to catch that type of thing and to understand what's going on. The same goes for if you have an average tenure of 5.4 years, but the standard deviation is 20.7. Once again, once we learn about these topics, that should set off red flags. That should set off alarms. There's something wrong about your data. There's something bad going on about your data. That if your standard deviation is that high with such a small mean, that would set off alarms that, hey, we need to fix this before we progress. And that's another reason why we need to learn descriptive statistics, is it can catch these problems with your data before you've wasted days, weeks, sometimes years doing more complicated analyses just to find out your data's messed up. Okay. Also, another reason why we need to know descriptive statistics is in practical applications. Practitioners are sometimes most interested in descriptive statistics. As y'all know, in business, a lot of people don't know statistics. In industry, a lot of managers don't know statistics. So if you present anything more complicated than a mean, median, standard deviation, some people might not know what you're going to talk about. So therefore, if you understand descriptive statistics and you can make your argument with descriptive statistics, that can help ensure that more people understand what you're talking about. That can help you ensure that more people can understand your results. Okay. So whereas inferential statistics might be confusing to some people, descriptive statistics are straightforward and most people can understand descriptive statistics. It's pretty safe to assume people can understand descriptive statistics. Sorry, my cat's biting my webcam. Give me one sec. Okay, sorry about that. Like I said, my cat was biting my webcam cord, so didn't want that to happen. Okay, so descriptive statistics, inferential statistics. Also, if you're into research, if you want to do research, every article is going to have means and standard deviations. So you cannot do business research unless you know descriptive statistics. So if you're ever wanting to go get your PhD in business or in something like psychology, a lot of the social sciences, you're going to have to know how to do descriptive statistics, because every research article is going to be expected to provide mean, standard deviation, things like that. Okay, so first we're going to start with measures of central tendency. Can anyone tell me what the 3 most common measures of central tendency are?
Mean, median, and mode.
Yep, there you go. Good job. So the 3 most common measures of central tendency are mean, median, and mode. And we'll talk about all 3. So the first one is mean. So the mean also means the average. So I'm sure everyone in here is already familiar with mean. So mean also means the average, and it's the most popular measure of central tendency. It is the most popular measure of central tendency. So the mean describes the most typical or most expected value of the data set. So in theory, if you were to pick a random number out of your data set, your mean would be the closest value to that number on average. So your mean is the most typical or most expected value in your data set. That if you were to pick a random number from your data set, on average, the mean is going to be the closest value to that number. Also important things to note is that mean is represented by X bar. So if you ever see a research article, or if you ever see something I give you for this class, and you see that X bar is written somewhere, that just means the mean. So if you see X bar equals something like 7, that just means the mean is 7. So X bar just means the mean. So X bar equals 7 just means the mean is 7. This is the statistical formula for mean. So this is the statistical formula, and you can see it's every number in the data set, or sorry, every number for that variable in your data set. So every number for that variable in your data set divided by the total number of observations for that variable. So it's every number or every observation for that variable in your data set added together, divided by the total number of observations for that variable in your data set. Okay. Do we need to memorize formulas? That is a good question. You do not need to memorize the, let me think about that. Do you need to memorize formulas? You need to know what the parts of the formula mean. So if I were to do something like give you this right here and tell you to label that formula, you should be able to label it. So let's go ahead and do that together. So if I were to give you this right here, the circled formula, I would expect you to be able to label each part of that. So the first part I would expect you to know is this right here. So can anyone tell me what that is and what that means?
Summation.
Yep, it's summation. So that is the sigma. So that is sigma, and it is summation. It is the sum. So good job for iPhone who said that, whoever that is, and good job for the 2 people in chat. So that symbol in the square is called sigma, and that just means the sum. That just means you're taking the sum. Okay. So what is this right here? What does that represent? The values, yep, that's correct. So good job, Vanessa. So this xi is all the values of x. So this represents all the values of x. So the top part of this formula, just is the summation of all the values of x. So sigma x of I just means the summation of all the values of x. And then what is, give me one sec. So then the last part of this that I would expect you to know or to be able to label is this right here. What is that right there in the box?
Total number of observations.
Yep, the number of observations or the sample size. Completely correct. The number of observations or the sample size. So in short, the formula for mean is simply sigma, or the summation of all of the x values or all of your x observations divided by the number of observations or your sample size for that variable. So if I were to, I would think it's reasonable to expect y'all that if on a test perhaps, I could give you something like this entire formula, And I could say there are 3 important parts to this formula, label those 3 parts. So you would be expected to be able to identify sigma, x of I, and n as the important parts, and then tell me that means the summation of all the observations divided by the sample size, or the total number of observations. So that was a very good question. So thank you for that question. Are there any other questions or comments about this? Okay, so I'm clearing. And let's continue. Okay, so this is a visual representation, of what the mean might look like. So once again, this is just a histogram. We can see it's relatively normally distributed. And the mean is the dotted line that in this example, the mean I believe was about 4.2 for this data set. And we would probably assume that this is a pretty accurate representation of the central value of this data set. So once again, the mean is an indicator of central tendency. It should give us a representation of the middle value or the average value, what we would expect the middle of the data set to be. And this is a pretty good representation for this example. Sometimes, however, the mean can be a little bit misleading. That in an example like this, none of the values are anywhere close to that middle. None of the values are close to the mean because this is a bimodal distribution. This is a bimodal distribution. That we see that all of the values are either 1 to 3 or they're 5 to 7. However, since they're evenly distributed like this, our mean is 4. So sometimes you can get a mean value because this is the correct mean. You can get a measure of central tendency that's actually nowhere close to any of the values, such as a bimodal distribution. So in this case, if you have a bimodal distribution, your measure of central tendency could be misleading because none of our values are 4. However, that's what our mean is. That's what our resultant mean is, our resultant indicator of central tendency, even though none of the values are this number right here. Another example of when the mean can be somewhat misleading is when you have outliers, when your data is skewed. So your data could be skewed. You could have outliers. So in this example, we have 2 outliers out here at 19 and 20. And even though most of our data falls over here, even though most of our data is somewhere like around there, our mean is moved up a little bit. Our mean is moved up a little bit. And that's one thing to remember about the mean, is the mean is sensitive to outliers. The mean is sensitive to outliers. And that's something important to know. That whenever you're looking at your mean, whenever you're calculating your mean can be drastically shifted due to outliers. So sometimes when you have outliers, your mean is not the best measure of central tendency. It is the most popular. It is very good. It works most of the time, but sometimes the mean can be misleading, such as a bimodal distribution or such as outliers or skewed data. So therefore, let's talk about the next one. The next one is the median. And the median is the value that falls in the middle of the data set. So the median is the value that falls in the middle of the data set. So your median is quite literally rearranging the values in your data set from smallest to largest and picking the value that falls in the middle So you just rearrange your data set from smallest to largest and you just pick the value that falls in the middle. What happens if that falls between 2 values? And the answer is you take the average of those 2 values. So sometimes when you have an even number of values in your data set, you just take the average of the 2 middle values. If you have an odd number of observations in your data set, you just pick the middle value. It's easy as that. Okay. Yeah, so here's an example of median. So once again, this is the same examples we looked at before. So we have a relatively normal distribution. This data set had an even number of values. So the middle of it landed between 4 and 5. So the 2 middle numbers of this were 4 and 5 because we had 2 numbers that fell in the middle. And in this example, the median was 4.5. And that's pretty accurate. We're going to be pretty okay with that. That's pretty close to what we would expect the central tendency to actually be. Here's another example. You can see the median can still be misleading in some cases. So once again, bimodal distribution. So even though none of the values were 4, even though none of the values were 4, the two middle values were 3 and 5 when we arranged the data set from smallest to largest. So we take the average of 3 and 5, and even though none of the values were 4, we get a median of 4. Even though none of the values were 4, we get a median of 4. So once again, median, sometimes it can be useful, but sometimes it can be misleading, such as in this example. One instance that median is particularly helpful, though, is when you have those outliers. So the median is resistant to outliers. The median is resistant to outliers. And that is one important thing to know. The median is resistant to outliers. So in this example, we would expect the central tendency to be somewhere over here. And we do see that if we arrange the data set from smallest to largest, the median was in fact 1, because the middle value, when you arrange this from smallest to largest, was 1. And we see that over here. So even though we have 2 outliers way over here, that didn't shift our median. That did not change our median. So the median is resistant to outliers. Okay. So that's all about median. Are there any questions about median so far? Or I guess mean, or anything else we've covered? Okay, so let's continue then, and let's talk about mode. And mode is just simply the number that appears the most. So mode is just the number that appears the most. We're not going to use it that often, but sometimes it does have importance, so we should cover it. Okay, so once again, in this example, we can see that in this data set, the number that appears the most is 4. So therefore, the mode is 4. So in this case, the mode did get pretty close to our center, what we would expect the center to be. In the bimodal distribution, our mode is actually, both 1 and 7. So this is an important instance that can happen, is if you have 2 values that appear equally as often, the mode is both of them. If you have 2 values that appear equally as often, the mode is both of them. So in this example, our mode is both 1 and 7. So this is one instance where the mode is different than the mean and the median. And if you remember, the mean and the median before was 4. In this case, the mode is both 1 and 7. And that tends to work better, or that ended up working better for this data set. That ended up working better for these observations. It doesn't always work out better, but in this case it did. Okay. And lastly, this is the mode for this data set. Once again, the mode is resistant to outliers. The mode is resistant to outliers. So 1 was the most common value, so therefore the mode was 1. 1 is the most common value, so therefore the mode was 1. Okay, so what do we normally do in practice? Normally, we almost always start by calculating the mean. If you're doing any type of analyses, people are probably going to expect you to report the means of your variables. So I would recommend always start with the mean. Always, always, always start with the mean, no matter what. Then if you think your data might be skewed for some reason, also go ahead and calculate the median. So if you think your data might be skewed, if you think you might have outliers, go ahead and calculate the median. Because as we talked about, the median is resistant to outliers. It is resistant to skew. So start with the mean. If you think your data is skewed or has outliers, calculate the median. And then we rarely calculate the mode. I don't think I've ever calculated the mode for really anything in my life. So I'm sure some people find it useful. I never really have. So, but we should learn how to do it anyways. Okay. So any questions about mean, median, or mode? Any questions at all? Okay, so let's see how well this works. I wanted to try this today to see how well this would work over Zoom. So part of this class, oops, let's not look at that. So part of this class is I want us to do experiential learning. So I want y'all to try to do things first, and then we'll talk about it as a group to see whether you were able to figure it out or not. So I want us to break out into groups and to calculate the mean, median, and mode of the descriptive statistics data sets in, that's a Sakai, that should say Canvas. So in Canvas, there's 3 data sets for descriptive statistics. I'm going to break us out into groups, and I want you to first try on your own to calculate mean, median, and mode using these descriptive statistics data sets. So I'm going to go ahead and see if this works and try to break you all into breakout groups. So you're going to be in about 6-person groups, and I want you all to work together as a group. Whether that means one person does it and show everyone else, sure, do that. Or if that means everyone work together to figure it out, you could do that too. But in some way, I want y'all to try to first figure out how to do it on your own, and then we'll come back as a group and see were y'all able to do it. So I'm gonna break y'all out into groups. I'm gonna do it randomly and see if that works. Hopefully there's enough people that are paying attention that will actually work in a group. But if not, hey, that's a lesson for me. At least we figured it out on day 2 and not later in the semester. So I am now breaking y'all out into groups. It's going to be about 5 people in each group. Let's make it about 6 in each group instead. Okay, so I am breaking y'all out right now. I will bounce around for the groups. I will be looking at the chat window, so if anything weird happens, just send me a chat message and I'll come to your group. So go ahead, download the Descriptive statistics data sets off of Canvas. Try to calculate mean, median, and mode on your own, and then we'll come back together and talk about how that went for y'all. And I'm trying to move all participants to breakout room. Okay, did y'all get an invite to the breakout rooms? Let's see if that works. Oops. No, give me one sec. Oh, there we go. Okay, so you should have been invited. So go ahead, join your room. Oh, look at that. Y'all are actually paying attention. Good job.
Hey, Dr. Howard. Hello, Dr. Howard.
Okay, I think we're all back in the main room. So good job. I bounced around from room to room. It seems like everyone was participating together. Some in different forms. It was interesting to see some groups all turn their cameras on, other groups kept it off, but it seems like y'all were able to get it. So good job. These were the, these were the numbers you should have gotten. So hopefully you were able to get those numbers. Two things I wanted to point out is I noticed that a lot of the groups did the like equal, average, open parenthesis, highlight. That's perfectly fine. That's wonderful. That works for mean, median, and mode. Later in the semester, we will learn how to use the data analysis add-on. So if you don't know how to use the data analysis add-on, we will learn that later in the semester, and that will make it, in my opinion, much easier. So if you're using the equal syntax way, that's perfectly fine. That gives you the correct answer. But we will learn the data analysis add-on approach. Another thing I wanted to note is, as you'll see with data set 3, there were 2 different modes. So Excel is awful at finding 2 different modes. It is terrible. It is not programmed well to do that at all. So therefore, I made a guide on matsyhoward.com. If you ever in a situation where you think you have multiple modes, be sure to check out that guide. Once again, this PowerPoint is on Canvas. So if you need that link, just go to the PowerPoint on Canvas, because there's a really roundabout way you have to use to get Excel to give you multiple modes. You have to like highlight things, type in the right command, hold down the right buttons when you hit enter. So long story short, it's really hard to get multiple modes in Excel. So be sure to check out that guide if you need help with that. Was there any questions or comments that y'all had about calculating mean, median, or mode? I tried to answer questions in groups as I came to them, but any questions or comments about that? Okay, like I said, it seems like everyone got it, so I'm happy about that. Very happy about that. Okay, so now let's go ahead and progress into percentiles. This is something that probably everyone has heard about. So in addition to central tendency and dispersion, which we'll talk about dispersion next, we're sometimes interested in percentiles. So there's 2 popular definitions for percentiles, and your book actually uses a 3rd one. This is something I was not aware of the first time I taught this. So the first time I taught this, I gave a definition that I use, and then everyone in class said, well, that's not what the book says, and it went terribly. So now I know, now I can go better. So the first definition that's common is a percentile is a measure that tells us what % of the total frequency that's scored at or below, aka less than or equal to that measure. Whereas definition 2 is a measure that tells us what % of the total frequency that's scored below, aka less than that measure. So the difference is really just, is it less than or equal to, or is it just less than? The definition we're going to use, or sorry, the book actually gives another definition. The book says in percentile divides the data set into 2 parts. Approximately P% of the observations have values less than the percentile, and then 100 minus P% have values greater than the P percentile. So the definition we're going to use for this class, because all these are technically correct, is more along the book definition. I know the book definition is weird. I don't really like the book definition, but we have to use the book, or we have to go by what the book says. So a percentile is a measure that divides the data set into 2 parts, such as a certain percentage scored below the measure and 100 minus that percentage scored at or above that measure. So pretty much you just have to remember that a percentile is the percentage that's scored below that measure. So if you're in the 90th percentile, that means 90% of people scored below you. If you're in the 50th percentile, that means 50% of people scored below you. And if you're in the 10th percentile, that means only 10% of people scored below you. And once again, this is pretty much a rewording of the book definition. So if you're ever confused about this and you have a copy of the textbook, just refer to the textbook. I will acknowledge the chapter in the textbook about percentiles, or the section about percentiles in the textbook, isn't that great. And I'll give you more resources at the end of this little part of the lecture. Okay, so hopefully that helps us with the definition. Once again, if you get confused, refer to the PowerPoint. But it also turns out there's 2 popular formulas to calculate percentiles. So once again, when I started teaching this, I thought there was 1 definition, 1 formula. Turns out there's 2 popular definitions, 2 popular formulas, and there's several other unpopular formulas. In fact, one time I looked into it, and apparently there's at least 17 different types of formulas to calculate percentiles. I have no idea why. I have no idea who would waste their time thinking of new definition or new formulas to calculate percentiles, but there's people out there that spend their time on that. So for this class, we're going to use the following formula. The formula is your sample size plus 1 times your percentile you're interested in divided by 100. So once again, n plus 1 times p divided by 100, whereas n is our sample size and p is our desired percentile. And once again, this is the same as our textbook. That's why we're going with this formula. And there's more information about it. I'll go ahead, and if you're getting worried about this, I'll stop you from getting worried. I'm never going to expect you to use this formula. I'm never going to expect you to apply this formula. We'll talk about doing this in Excel in a second, but this is something you should know. You should be aware of this, of how this works. So applying this formula, if our sample size was 99, and we wanted to determine the 10th percentile of our sample or of our variable, the formula would simply be we plug in the sample size for n, so it'd be 99 plus 1 times, and then we plug in what percentile we're interested in for p, so it'd be 99 plus 1 times 10 divided by 100. So that turns into 100 times 0.1, so that turns into 100 times 0.1, and then when you multiply those together, you get 10. So that indicates that the 10th value in your ordered data set is the desired percentile value. So that means you would just order your data set from smallest to largest, find the 10th value, and that is your 10th percentile value. That would be your 10th percentile value. So you would just order your data set from smallest to largest, find the number that is the result of that formula, and that's your percentile cutoff. Is you find the number in the ordered data set that is the result of that formula, and that is your percentile cutoff. I'm only going to expect you to know how to do this via Excel. I'm never going to expect you to do this by hand because no one should have to do that by hand. The way I just now told you is the formula that equals percentile.exe uses in Excel. So if you're using Excel and wanting to calculate percentiles, you would just type in equals percentile.exe, and then it is, let's see if I can draw on here again. Yeah. And then it is open parenthesis. You tell it what data you're looking at. So if you're wanting to do it for the first column, it would be A:A. So you tell it what data to look at. So if it's the first column, it would be A:A, and then comma, and then you tell it what percentile you're interested in. So if we're interested in the 10th percentile, it would be 0.1, and then close parenthesis. And that's how this function works, is it's equal percentile.exe, open parenthesis, you tell it what data to look at, comma, and then you tell it what percentile you're interested in. And in this case, we might be interested in the 10th percentile. So you would type in decimal point and then the number 1, and then close parenthesis. So that is the Excel function for the formula we're going to use in this class. You should be aware that the commands equal percentile and equal percentile.inc, they do use a different formula. So if you use these two commands, you're going to get different results than if you use this command. So be aware of that. Make sure you include that .exe on the end of that percentile command. And once again, we're using this percentile.exe because that's what our textbook uses, and I need to be consistent with the textbook. Okay, any questions about that? Any questions about that? Okay. So I know it can be a little bit confusing. So let's ask some questions. So first off, when we're talking about percentiles, if your boss told you you're in the 90th percentile performance, would you be happy about that? So if your boss tells you you're in the 90th percentile, would you be happy? See one person saying yes, and yeah, we would be happy. That means we're doing better than 90% of people. That means we're in the top 10%, we're doing better than 90% of people. So yeah, we would be happy about that. What if our doctor told us we're in the 50th percentile of health? Would we be happy about that? We would be so-so. We would probably want to do better. Of course, we want to be in the 99th percentile. So if they said we're in the 50th, that means we're average, we're better than 50% of people. We would feel so-so. And then lastly, how would you feel if your kid told you while jumping in for joy that they're in the 10th percentile on SAT scores? How would you feel about that? Probably not too happy. Exactly. You would be wondering, all right, why are you jumping for joy? You're only better than 10% of people. You probably need to work a little bit harder on that. like one person says, bless their heart. That's the good Southern way to put it. We would say bless their heart and help them do better. Yeah, and go ahead and spend their college fund, that too. Definitely options we would want to consider. So I'm glad statistics is teaching us good ethical things to do. So good job on that. Okay, so if you're still confused, now I know percentiles can be confusing. MattCHoward.com does have a statistics help guide on percentiles because, like I said, the first time I taught this, I thought there was one definition, I thought there was one formula, I thought there was one way to do it in Excel, and then the textbook did a completely different way. So if you're confused about this whatsoever, please check out my website. It has information about it. I've spent a lot of time making that guide. Other colleges and universities use that guide, so I think it's pretty helpful. So if you're confused about this, be sure to check out that webpage. And once again, these PowerPoints are on Canvas, so you can find that link in the PowerPoint on Canvas. Okay, let's go ahead and do this to end class. I'm going to go ahead and break you all into groups again, but if you want to do it on your own, don't feel the need to necessarily have to interact with your group, unless you need help or unless your group wants to interact. Y'all might be friendly. But go ahead and on the same in-class data sets I sent you, go ahead and calculate the 10th, 50th, and 90th percentile of the variables of those data sets. And once again, I already have given you all the results. So these should be the results you get. So go ahead and on those data sets, try to calculate the percentiles, see if you can get these results. And I guess quick show of hands, do y'all want to break out into groups or do you just want to try it on your own? I see one person saying no on groups. All right, and this is a good opportunity for me to practice this. Add a question. Let's see if I can do this. Give me 1 second. Oops. Give me 1 second. I'm trying to set up a poll. This is a good thing for us to practice. Do we want to do groups? Solo, group. Okay, so let's see. Save. Polls, launch polling. All right, did y'all get a poll just now? Hey, look at that, that's working. Learning something new every day. Okay, so it looks like the vast majority want to do it solo. Let's go ahead and do it. So go ahead, let's do it solo. If you need help, just ask in the chat or send a private message to me and I'll help. So go ahead, see if you can calculate these percentiles on your own because that's what the vast majority of the class wants to do. And if you need help, just ask in chat. And that's how we're going to end class today. So go ahead, try to do it on your own, and then we'll talk about it together. I see one person in chat asking about an Excel crash course. So there are the links on my website. I'll go ahead and send those out. I also also have videos. I'll send out a video. I cover descriptive statistics when I teach this in my undergrad stats course. So I'll go ahead and send out the video that I recorded for my undergrad stats lecture. So I'll send y'all resources for this too. So if you're not picking up or understanding mean, median, and mode, percentiles, I will send out those videos. So I'm glad you appreciate that. All right, so go ahead, try to do percentiles on your own. Once you feel comfortable with it, y'all can go ahead, leave class. So thank y'all for hanging in there. Thank y'all for listening to the lecture. I'm going to be here for the last 10, 15 minutes. So if you need help, just feel free to ask. But otherwise, once you feel good, you're free to go. And thank y'all. Thank y'all for listening today.
I have one more question for you.
Yes, feel free to ask it.
Is there any way that along with that video, I guess you could give us a general understanding of what we will need to know how to do in Excel, just so that I'm, aware.
Yeah, are you talking about for like test purposes or?
Just in general, just for general knowledge in this course, I guess.
Yeah, that's a good question. So yes, I'll say before the midterm, it's going to be very little in Excel, just because I think the midterm, usually I give it paper. Now that we're doing it a little bit differently, I might have a question or two that involves Excel. So for the midterm, it's going to be just pretty much descriptive statistics and percentiles. It's not till after the midterm, you're going to need to know correlation and all the other stuff. And I'll be very clear about that after the midterm.
Okay, perfect. I'm definitely going to need a crash course in here. So.
Yeah, no, that's a good, and I'm trying to think. I might try to figure out time to give a more focused lecture on using Excel, because also because since we're using a stats program I've never used before, well, I've used it before, but never taught it before in Jamovi. That's going to require also some like moving data around in the data set. So that could be helpful for me to teach y'all. So thank you for bringing that up.
Yeah, thank you. I appreciate your help.
I'm writing it down right now.
That stats database, will we be using that now?
So right now you can use Excel. Just using Excel for now is perfectly fine, and that's what I would recommend. I don't think there's a reason to use Jamovi at the present moment. And using Excel, you do not need to reformat your database or anything. You can do the analyses just as they are.
Okay, so I'll need the database possibly after midterms.
Well, so the program Jamovi is completely free. So I would say don't worry about it for now. I'll give instructions on how to download Jamovi after the midterm.
Okay, awesome.
Yep. Someone asked, when you were discussing mean, median, and mode, what was the term used for the charts that are divided by modal? I think I just called them a bimodal distribution. So that was, I think, the term I used. If anyone knows of a different term I was using, them, please feel free to speak up. But I think I was just calling it a bimodal distribution. Also, someone asked, what chapters do we need to complete to be ready for the first homework? That's a good question. The first homework, let me log on real quick to Canvas. I believe the first homework is just descriptive statistics alone. So after Monday's lecture, you should be able to do homework 1. Yep. So I'm logging in right now to double check on the homework to make sure I'm correct about that. Student view, assignments. Yeah, so homework 1, yeah, it's about visualizing your data a little bit, mean, median, and mode, standard deviation. Oh, and it does include percentiles. So yeah, so actually you could, yeah, you could actually probably get it done. Oh, you still need standard deviation. So yeah, after Monday, you should be able to do homework 1. So that should answer that question. And then someone asked, not sure if everyone else has the same question, but when it's not an integer, is there an extra step? It depends on what you mean by not an integer.
Well, I see on your website, there's 3 different formulas you could use that come up with 3 different answers. So I guess, I mean, for the Excel one, it comes up, I read somewhere, I was reading in the book, it says you have to do, like, if it's not, it needs to be an integer, or you have to do difference between the 2.
I'll have to look into that.
Okay. But like for the homework purposes, if it comes up as a decimal point with, as a non-integer, that's fine, right?
Okay, I see what you're saying. Yeah, that's fine. Yeah, that's perfectly fine. If it's a decimal point, just always for everything, it's perfectly fine just to include 2 decimal places. and just put in exactly what Excel tells you up to do 2 decimal places.
Okay.
Yep. Yeah, I see what you're saying now.
But yeah, it has this definition in the book where it talks about if you get an integer and if you don't get an integer, what to do. So I didn't know if that was,
yeah, that's one thing I skip with this lecture, just because I feel like the book overly complicates percentiles. And that's the thing that when I first taught this class gave me a lot of difficulties is I didn't expect the book to like get that thorough about percentiles. So I just try to make it as easy as possible.
Yeah, I've only learned it the way that you just showed us. So I didn't, when I read the book, I got a little kind of like, well, I don't know this other way. So.
Yeah. So no, I mean, I do statistics for a living. And even when I read the book section about percentiles, I'm like, all right, that doesn't really make much sense in some sections. So.
Okay. All right. I just want to double check. Thank you.
Of course. Okay, any final questions? All right, well, I am logging off. Thank you for hanging in there, and I will see you all on Monday.